So today's lecture is about state estimation. Up to now, in the laboratory in particular, you have been considering the situation in which the state is available for direct measurement. But this is not always so. There can be physical reasons. This slide shows one example that consists of estimating the state of a glass furnace. A glass furnace is a good example of where you are going to end if you don't succeed in doing well the laboratory report. You can see it's a lake or a pool of melted glass. Melted glass is essentially melted rock. And you see that there is a flame, okay? You see here on the left, there is a flame. So they are burning some fuel here, can be gas or can be a liquid fuel. And also injecting some air. And so this flame is producing heat that melts the stone powder that is entering from the side walls. This cannot be seen here, but there are places in the side walls of this furnace where the raw material is entering. It's basically some mineral powder, and it's melted. And from time to time, what happens is that you are injecting oxygen from this side to burn the fuel, and you are taking the exhaust gas from the other side, from the right, from this arch that you see here. And the exhaust gas, what results from combustion, is being heated, is heating a kind of, it's a construction made of hollow bricks. So like the constructions of bees, favo feito em tijolos especiais que aquece. So during part of the operation, the air is entering and passes through one section of these hollow bricks. So the air enters not at ambient temperature, but it's already heated. And at the same time, the exhaust gases are heating this section on the right. And then this is switched. Okay. What is important here is that the state is the temperature along the pool, the glass pool. And the glass pool is, you can consider a grid of points inside the glass pool. And the problem is that the glass pool is at temperature of the order of 1100 degrees Celsius. So it's not possible to go there and measure inside the glass pool the temperature. You can only measure the temperature at the top of the furnace, below the furnace, and so below the floor of the furnace, and at the surface using optical means. That's but inside the pool of glass melted glass, you cannot measure temperature. So you cannot have access to the state. You cannot measure the state here. It's technically impossible. So you will have to estimate it. Another example where you can't have access to the state, you can't measure the state, is when your state has only a mathematical meaning. In many cases, the state, you know that if you do linear transform of the state, you still have a state. And you can have states that have no physical meaning, but only a mathematical meaning. And this means that you cannot have a sensor that measures it. So again, you can only estimate it. And I've included also here the situation in which you have a state corrupted by noise and you want to minimize the effects of the noise on your measurements. So these type of situations, and perhaps more situations, for instance, SLAM, with which some of you are familiar, simultaneous localization and mapping. So you have a robot, and the robot wants to find out by observations of where he is, and at the same time wants to improve the map of the environment. And again, there you need some state estimators to solve this problem. So if you think of this in relation to MPC, of course, you have the MPC controller, this block. The MPC controller receives the state, but since you don't have the state, you have an estimate of the state. I put a hat symbol over the state to show that this is not a real direct measurement of the state, but it is a measurement, an estimate. Sorry, it is an estimate of the state produced by a state estimator. That's the subject of this class here. And the state estimator uses the information from the input of the plant, the output of the plant to build X hat, the estimate. And then the MPC generates U based on this estimate and on the reference. In the case that you are considering at the lab, you are assuming, yes. In the case that you are considering at the lab, we are assuming that we are measuring directly the state, so we don't bother about state estimation. So today's lecture is about state estimation. Now, let's start by considering a situation in which we have a linear plant, okay? And the linear plant, well, I should have written here another slide. What is the model? The model of the dynamic plant is look at this equation and get rid of this KO, etc. Okay, so I will correct this in the final version of the slides. So the next state at k plus 1, forget about this given k, is the dynamics of the dynamic matrix of the system times the previous state plus gamma UK. Okay, and we are assuming that we know this dynamic matrix that I call phi, and this vector that multiplies the input that I know gamma. So we want the game of the state estimator is to observe Y, observe U, and estimate X set. Okay. So one possibility is to do this. We do a replica of our system. That is to say, X hat of k plus 1. Ignore for the moment this given k, because the estimate of the state at time k plus 1 is a replica of the system. So it's just a copy of the dynamics of the system. Phi X hat of k plus gamma UK. Okay, now it's not difficult to see that if you have just this replica, you wouldn't be able, for instance, to estimate, to make the error, the estimation error, the difference between X hat and X, to converge to to 0, to make the error, the estimation error, to converge to 0. If phi is an unstable dynamics, then this error would diverge. So someone had the idea of correcting the estimate by this term. Look at what is here. Y of k is the output of the plant that you are measuring. And x hat of k is the estimate at time k. So Cx hat of k is what you are expecting y to be, because y of k is Cx hat. Sorry, y of k is Cx. So C times the true state. So we replace the true state by our estimate. If our estimate is good, this is approximately 0. And the state evolves according to the replica of the dynamics. But if there is an error, then this term here will act in a way that corrects the error. Okay, this k0 is a gain. Okay, in a moment we are going to see how can we find out this KO. So let's define sorry, just a moment before going on. Why do I have this bar, this conditioning on k minus 1 and here on k? Okay, so this bar means x hat, the estimate of the state at time k plus 1, given the information up to time k. If you look here, I'm computing the estimate of the state at time k plus 1 based on what? On the previous estimate at time k, on uk, and on yk. So the estimate at time k plus 1 depends on the previous value observed for the output. That's why I call this a predictive observer, because I'm making a kind of prediction of the next state given the model, and also this correction term associated to the output. Okay, so probably if we are at time, suppose that we write this instead of k plus 1, I put here k, so that's k given k minus 1. Here, that's k given k minus 1 given k minus 2, and so on. Okay. Now, suppose that you want to get the estimate at the time where you are. So you want to have an estimate of the state at some given time, say k plus 1, given the observations up to k plus 1. Okay. Later we will be seeing how we can do this. So this, for the moment, is what we call a predictive observer, and it's very simple. It's just a replica of the dynamics of the system plus a correction that depends on the output. Okay, so let's do some analysis of this estimator. I define x tilde to be the difference between the true state and the estimate of the state. So this happens at any time, and the time is the same for all these variables, so I've omitted the variables. Now, I have my model, x of k plus 1 equals to phi of x of k plus gamma uk. This is how I'm assuming that the state evolves. And now I have the equation of the observer. Okay. Now, if I subtract these equations, what happens? Gamma uk cancels with gamma uk. Then you have phi xk and phi x hat. So when you subtract these two terms, you get phi x tilde. And here y is cx. So this is ko c x tilde. Okay, so you end up with this equation. Okay, so the error satisfies this equation here. The next error is phi minus koc. This is a matrix. And this is a matrix that I can influence because I can select KO times X tilde of K. Okay. Now, what is the solution of this equation? Just iterate it. So whenever time passes, time sample passes, you just multiply by phi minus KOC. So in general, when you consider that K steps have passed after the initial time 0, you just have the K's power of phi minus KOC. Okay? And what you want is that this goes to 0. Okay? But this goes to 0 if it's posed its roots of the characteristic equation or the eigenvalues of this matrix, phi minus KOC, they are all inside unit circle. Because actually, this is, we don't do study that in depth, but and some of you know already this, some of you don't know, but take my word that this is nothing more than a linear combination of powers of K, where the powers are the eigenvalues of this matrix. Okay, so for this powers of the eigenvalues to go to 0, their modulus must be smaller than 1. Okay, so what do? You compute the characteristic polynomial of the observer. That's Zi minus the matrix, and the matrix is phi minus KOC, so Zi minus phi plus KOC. And you are going to select KO such that the eigenvalues of, or the roots of this polynomial are all inside the unit circle. Okay? So in that way, what you have your state, that's the empty bullets here, and you have your estimates. And you start with an estimate probably with a large error. That's the crosses, the estimates. And if you design your let's call it observer or state estimator, that's the same thing in this situation where we are considering no noise. So we can use observer also to call the state estimator. If you design your state observer such that you the eigenvalues of this matrix phi minus KOC are all smaller than 1 modulus in absolute value, then what happens is that this error is decreasing. Okay, it can even oscillate depending on the eigenvalues, of course, but the idea is that they are decreasing, and after a while, your estimate is tracking the true state. Yeah. So, any question up to now? I realize that for some of you, this has already been studied, so it's something that you saw already. For some of you, in particular, the ones that come from the first degree on aerospace engineering, this is not. This is a new thing. So, would you like to make some questions? Okay, so let's go on. You can ask me questions later if you want, and we can go back if you feel lost. So let's see one example. Suppose that we have the double integrator. Okay, could be any. I could have placed here any state model, but the double integrator is not nice because it's the dimension is not so big. The dimension is not so big. It's just 2. And it's a non-trivial problem. And I observe the output that corresponds to the position, and I want to estimate term of the state, which is the velocity. So I want to estimate the state from observations of just the first component of the state. That's the meaning here. Y, it's 1 times x1 plus 0 times x2. So y is just x1. And I want also to estimate x2. And I want now my specification. I want the roots of my polynomial observer, that is to say, the roots of this polynomial to be, to be at 0.4 plus or minus j 0.4. Okay? Now, how do I select these figures? Here it was quite arbitrary. You don't want it to be so close to the unit circle. So saying that I want my eigenvalues to be 0.9. Well, it's not a good choice because the error will depend as the power, will evolve as the power of these values. And if the value is quite close to 1, it decreases very, very slowly. So this means that this error, these sig bars, are going to decrease in a very slowly. It takes a long time to have a good estimate. On the other side, the more to the inside of the unit circle that you select these numbers, the faster the estimate will be. Okay? And of course, this gain KO will increase because you are going to displace the eigenvalues of phi for bigger and bigger values. So KO will have to increase. But this is usually not a problem numerically. The problem that we should bear in mind is that in a general case, in a real case, our model is just an approximation. So if you have a very fast observer, that is to say, an estimator that converges very, very fast to the true value, this is elusive because you can have divergence due to the modeling estimation errors. Okay, so bear this in mind. So here I've selected this and take it for, let's take it for granted. So we have first of all, we must write down a desired characteristic polynomial, which is a polynomial that has these roots 0.4 plus or minus j 0.4. Okay, so this is results from nothing more than z minus 0.4 minus j 0.4 times z minus 0.4 plus j 0.4. Okay. Okay, so this is my desired characteristic polynomial for the error dynamics. And then I write this characteristic polynomial that is the dynamics of the error. Okay, so zi is just z times the identity minus phi. So I put here the phi matrix, okay, of the model. This is the phi matrix. Sometimes I also call it A. Plus KO, 2 components, C, and C is 1, 0 again from the model. And I compute this determinant, I do all the computations, and I correct my errors that will certainly appear when I do this with pencil and paper, and I get this polynomial. Now, to find out the values of the gain KO, I just equate the coefficients, the corresponding coefficients of the different powers of Z, of the polynomials of Z. So Z squared has a coefficient 1, okay. Here I also have 1. Then KO1 minus 2 should be equal to minus 0.8. So I get one equation. And then I have, this is a constant, H KO2 plus 1 minus KO1, that's 0.32. And I get a different equation. And if I solve these two equations, I get the values of KO and K2. Okay. Now, there is software in MATLAB for doing this, for designing this polynomial, these games. I will not speak about it here. Any question about this example? You might ask whether I end up with a linear system that has a solution for KO and K2. Sometimes I have more if my state, if you are considering oil drilling platform, the dimension of the state is 500. Okay, so am I able to find out a solution for 500 linear equations? Or if it is an integrated circuit, it can be 1 million when you have 1 million state variables, say in a microcomputer. The condition is very simple, is that this C matrix here and this A phi matrix must be, this pair must be observable. You remember I mentioned to you the concept of observability, and we had even a criteria of observability. So this must be observable. Okay, if they are observable, it is okay. So before you do the computations, you could do this check just to ensure that your problem has a solution. Okay. Now, up to now, we have been considering, you see, let's write it again. This is the so-called predictive observer. So it's a replica plus a term that depends on the previous observation of K. Okay, so I'm updating the estimate of the state at time K plus 1 based on the observations of K. That's why I call it predictive. I could have considered a different version in which what I do is to have an estimate at time K given the observations of Y at time K. Okay, so I have still another value of Y. Sorry. So how can I do this? Again, I have a replica of my system. Now, instead of writing this in terms of K plus 1 given K plus 1, I'm at time K, so I want to have the estimate at time K, and I use the previous estimate. So this is a replica of my system. And then I should have KO, YK, and if YK goes with C times X hat of K, but X hat of K is something that I'm trying to compute. So instead of putting here X hat of K given K, what I do is again to use the dynamics, okay? So I replace in the formula X hat of K that this would result in an equation that would be very hard to solve. Possibly in many cases it would not be possible to solve it, if not in all cases. So I replace this X hat of K by what X hat of K would be given the model. Okay, so that's how we write the so-called current observer. Okay, so that's it. Now, we can write the equations in this way. Okay, these two equations are equivalent to both previous ones. I'm not going through all the details, but these two equations are actually equivalent to the previous ones, in which x bar is the predictive estimate of x. So this gives me the estimate of x at time k plus 1 given observations up to time k. So I have omitted the vertical bar here to simplify notation. And I have a correction. Now, these two equations, algebraically, you can recover both observers that we have before. If you eliminate x hat and just express everything on x bar, the predictive observer, you will get the equation for the predictive observer. If you eliminate x bar and express everything on x hat in this equation, then you get just the equation of the predictive observer that we have computed, that we have presented in the previous slide. Okay? Now, that's the algebra. But what is really nice is that we can give an interpretation here. So if you are at time k and you have a previous prediction, then you just replicate your model. And you have a filter. It's correct to say it's a filter, but I won't want to use the word. So if you have a current estimate, then you just use your model to make a prediction of what the state will be. Okay, we call this the prediction operation, and then you receive your last observation like A, and you correct your prediction by this term here, which is proportional to the error between yk and cx bar. Okay, there is a bracket here. Okay, and you can represent these equations according to this block diagram where z minus 1 means a delay, and all the rest means the symbols that appear there. And this is quite practical for implementing these equations in a, say, in simile, for instance. Now, this is quite interesting because these operations of prediction and correction, so you do a prediction based on your dynamics, and you do a correction or filtering based on your observation. Okay? This will appear when we consider more complicated cases, even in the nonlinear case. Any question? Okay, let's go on. Now, before moving to more general cases, I would like to call your attention to the fact that these observers or state estimators are filters. Okay, so what is a filter for an electrical engineering, and I think also for a mechanical engineering or even an airspace engineer? A filter is something you think of. You can represent your signals as a time function, but you also can represent your signals in the frequency domain. Okay, so you have these two domains, time and frequency domain. And so your signal has frequency content. For instance, when I'm speaking, I would speak if you decompose in sinusoids my speech signal, you will find values, you will find power, between, say, 200 hertz or 300 hertz and 3 or 4 kilohertz. Okay, so signals has given bandwidth, and in this case, signals are shaped by the dynamics of the system, of the linear system, of the state system. Now, suppose up to now we have not considered noise. We have not yet considered noise. But suppose that we add noise to our observations. Okay, so there is a range of frequencies in which the signals depend on the dynamics. That's typically low pass, some low pass bandwidths. That's the bandwidth of your system. And then you have a noise which is white, that is to say, it appears with an equal power density all over the spectrum. Okay, white noise is a noise that has that is constant from minus infinity to plus infinity in the frequency. Okay, in many cases you don't have white noise, but you have wideband noise. Now, if you want to estimate your signal, you should concentrate in the range of frequencies where the dynamics is significant. Because if you have higher bandwidths for your estimator, then what happens is that what is important in terms of frequency content of your dynamics has already been passed, entered, your received by you, say entered your controller, for instance. But if you have extra bandwidths, you gain virtually nothing in terms of the improving the dynamics, but you only receive noise. Okay, so one should optimize the bandwidths. One should optimize the bandwidths to according to the noise that we have, okay? And such that too much bandwidth of your filter. Okay, think of the observer or the state estimator as a filter. Okay, if you design it to have very big bandwidths, then you are just getting high frequency noise samples that degrade your estimate. If your bandwidth is too small, you are distorting the signal, so the dynamics of the plant is not seen fully. Okay? So there is a compromise. There is a compromise. And how do you adjust the observer bandwidth? You adjust the observer bandwidth by adjusting the observer gain. Okay, so you, for instance, in the predictive observer, you have to select this KO, and this KO depends on, you say, is the error going to zero faster or slower? Okay, the faster the error goes to zero means that your bandwidth is bigger. But when your bandwidth, when you are making your bandwidth to be very big, then you are also opening the window to let a lot of noise enter. Okay, so when you specify the desired closed loop or the eigenvalues for the error, okay, the eigenvalues for this matrix phi minus KOC, when you specify this the eigenvalues for this characteristic polynomial, the roots for this characteristic polynomial, if it is too fast, your observer is too fast, the bandwidth is too big, okay? And you are you are amplifying signals that just correspond to noise. Okay? If it is too small, then you don't let enough dynamics to pass. So there is a trade-off, and this trade-off is controlled by selecting KO. Okay. I'm sure that all of you have heard about Kalman filter or Kalman-Bussy filter. Okay. And the Kalman filter, we are going to see it in more detail, but the Kalman filter is something that does this optimization. Okay. So suppose that this is our model. Now I'm adding noise terms. So V1 of K is a kind of stochastic disturbance, and V2 of K is sensor noise. Remember that Y is related to X. This second equation is an equation related to the sensors, models the sensors, while the first equation models the dynamics. Okay, so V1 is process noise. Sometimes they call it process noise. It's disturbance, stochastic disturbances, and V2 is sensor noise. Okay? And we assume that they have some variances for stochastic state variances, QE and RE. Okay, so that's the power of these signals, of these stochastic signals. Now, we can think of this problem. I want to have an unbiased estimator. That is to say, when I compute the expectation, the expected error, the expected value of X minus X hat, this should be 0. That's the notion of an unbiased estimator. Okay, and it's easy. It's not difficult to see that we should use the observer structure. So that structure, in the linear case, gives you an unbiased estimator. And then you say, I want to minimize the steady state power or variance of the estimation error. So I do the sum, the expected value of the sum of the norm square of the error. This is the error, okay? So this is the power, the expected value of the power of there is a term missing here. There is one divide here. But this is essentially the power of the error, okay? And I want to select my hex hat such that this power is minimized, okay? And this gives me an equation or a procedure to compute the gain of the observer, that KO. Okay, I'm not going to show the equations now, but we will, before the end of this lecture, we will see. So one way of looking, there are many ways of looking at the Kalman filter. One way of looking at the Kalman filter is an observer, okay, where you optimize the gain. In practical terms, we can use this DLQE function, but I will discuss it a little bit more. Any questions? So we stop here for 8 minutes. So it's 2:52 or 2:51, I think. We will resume at 3 o'clock. Okay, so we do a small break here, and we will continue to examine these questions. Now, starting the program now is look at these problems from a probabilistic point of view in situations where we have noise, and get some equations that are very general, that cover the general case, that can even be nonlinear, and then particularize for the linear case, and we are going to get again the same equations of the Kalman filter, and doing some examples. That's the program for the next hour. Okay, so we will stop now and we resume at 3 o'clock. So I want now to look at these problems of state estimation from a probabilistic point of view. And usually you tend to be a little bit feared of when we use probabilities, but let's try to do things slowly and at least understand the main points. Probability is quite important, because if you can use probability to describe your knowledge. If you have a number of possibilities, you can associate different probabilities to each of these possibilities. If the possibilities correspond to a state, and the state is a continuous variable, then you have a probability density function, PDF, in Portuguese FDP. So the fact that probability allows you to describe knowledge is something that we should explore. Okay, let's consider a nonlinear model. X of t plus 1 is equal to f of xt. F is some function plus some noise, et. Okay? And then you have the model of the sensors. Y is equal to h of xt plus vt. Again, v is a sequence of independent and identically distributed values. So you can, the most popular case and very simple case is when you generate random numbers with a given distribution with MATLAB. Okay, so that's what we mean by ET and VT. And ET models stochastic disturbances that act on our system. For instance, if you have an aircraft and you have wind, then the wind has some probability distribution. The force of doing has some probability distribution. Then in some time, if you take samples of the force exerted on the aircraft, in sometimes you have higher force, then a smaller force, then a medium force, then some other value, and so on. Okay, that's the meaning of E and of E. And V is the sensor noise. Okay? So you don't observe exactly your function of the state H of X of T, but it is added by something that it's a random variable. Now, before I was working with an estimate, I was propagating an estimate of X. Now, what I want to do is, it's related, of course, and I will show you some relation in a moment. But it's a little bit more general. So I want to propagate in time. I want to know how to compute. T here is a discrete number. And I want to propagate the probability density function of the state xt given the observations. So this capital Y with the T on the top means what you see here. This technically from the mathematical point of view, this is the sigma algebra generated by all the observations up to time t. Okay? Why a sigma algebra? Sigma algebra is a set of sets, and probability has to do with measure theory. So to simplify things, assume that we want to combine probability, we want to compute probabilities of the state given the set of observations up to time t. Okay, and what do you do with that? If you know the probability of the state, then you can compute the expected value of the state, and you have an estimator. Okay, so this is one way of relating what we said before with the story of the propagating the probability density function of the state. So our problem is to suppose that you start with some probability of the state given the observations at time t. You receive an extra observation, and you want to compute the next probability density function of the state given the new set of observations that has an extra observation. Okay, so this is the perhaps in a more rigorous way. Suppose that you at time t you have computed before the probability of the state at the previous time t minus 1 given the observations up to time t minus 1. Okay, then you observe you do the current observations by t, and you want to combine yt with this conditional probability density function to get the updated probability density function of the state given the observations, the new set of observations. So how can we do this? How can we write equations for this square? I will be assuming that X is a Markov process. What is a Markov process? It's very simple. Look at this formula. A Markov process, suppose that you have some probability of some event, okay, given the state, a sequence of states, okay, xt1, xt2, xt1, up to xtn. If the process is Markov, what really counts is the last value of the state. So conditioning on all the states from T1 to up to Tn for a Markov process is just equal to conditioning up to on the state up to Tn. That is to say, a Markov process is such that the last value of the state has all the information needed to compute what is then going to happen. Okay, that's the notion of state. That's the notion of state. Okay, I've written here at the top the definition of state. For a deterministic system, it is a vector of variables such that if you know the control inputs in the plant model, if you know the state at one instant of time, it will be able to allow you, together with the input in the model, to compute what happens in the future. Okay. For instance, if you have a very simple mechanical system with Newtonian dynamics, say a material point, and the position of the material point is not a state, because it can have some velocity that points in one direction or the other. So if you know the forces, if you know the initial position of the point and the forces, you don't know what happens, what will happen in the future. A state in this case would be the position and the velocity. If you know the initial position and the initial velocity, then you will be able to compute. So that's the notion of state. Set of or vector of variables, such that if you know it in one time instant, you can compute what happens in the future, provided that you know the excitation of the system in the future. And the Markov process generalizes to the stochastic case this notion of state. So a state is something that gives you the fundamental information about the system, how the system is. Okay, and this formula is the same, but in probabilistic terms. So retain that for Markov processes, if you condition it on several instants of time, then what counts is just the last time. That's the important issue. Okay, now let me recall also two formulas from probability. One is, sometimes we call it the Bayes law. It's a formula about conditional probability. So if you compute a probability, this can be a probability or a probability density function of some variable A given observations of B. Okay, this is the same, and you multiply it by B, by the probability of B. This is the same as the joint probability function of A and B. Okay, so you can write the joint probability by decomposing into a conditional probability plus or times, sorry, the probability of the part in which we are conditioning. Okay, and this applies to several variables. Now, if we have another formula, is this one that we are going to use. If we have a joint probability of A and B, and you integrate on B, you just get the marginal probability PA. Okay, we are going to use this. So remember, let me go back. We know the probability of the state given the observations up to time t-1. And we do this observation, and we want to update, based on the observation, our density function of the state for the next time t. So we are going to do this in two steps: prediction and filtering. Okay? So in prediction, I'm computing the probability of the state at time t given the observations up to the previous moment, y of t-1. So remember that capital Y means the set of observations up to time t-1. So, and filtering is I receive the last observation YT, and from the predicted variable, predicted density function, I update it to build P of xt given YT. Okay, so let's see how we can obtain equations for these two steps or procedures. So let's start by prediction. So assume that at time t minus 1, you know the density function of the state at time t minus 1, given the observations up to time t minus 1. Okay? And now let's play a little bit with this observation, with this expressions for this density. Now, if I have P, the probability density function of xt, and xt minus 1, okay, conditional on something, if I integrate on on xt minus 1, then I get just the marginal. That's the formula. That's the second formula here. Okay, that's the second formula here. Now, let's isolate. Let's again use the first. Let's now use the first formula. So I have here the joint probability of xt and xt minus 1. So I write this joint probability as a conditional probability of xt given xt minus 1. Okay, this is already there, so I don't mention it. It will stay there. And I have to multiply by p of xt minus 1. Okay, that's the first formula. That's the first formula. Okay, I can write the joint probability density function as P of A conditional on B times PD. And that's what I've done here. Okay, this is this expression has a name. It's a Chapman-Kolmogorov equation. Okay, so I repeated that expression here, and now I use the fact that xt is a Markov process. So look here inside the integral. If I conditioned x on xt minus 1 and the observations up to time t minus 1, the observations of the time t minus 1 will depend on xt minus 1. Okay, it's already there. And then xt minus 2, xt minus 3, and so on. Okay, so I can just cancel out because xt minus 1 has all the information needed here. So I can replace this equation, this density, sorry, this conditional density, by just this one in which I've just made a conditioning on the xt minus 1. Okay, so I using the Markov process. So I place that story there and I get this equation. This is a kind, look, we have P of xt given xt minus 1. This has to do with the way the state evolves. The probability of the next state given the previous state. Okay, this depends on how the system evolves. And then here we have the density that we started. Okay, and this is a kind of convolution integral that defines the prediction. So I compute P of xt given the observations at time up to time t minus 1 from P of xt minus 1 given the observations of time t minus 1. Okay? So I do this multiplication with this term that depends on the dynamics, and then I do an integration. And that defines the prediction. Now, we have already seen how to, say, make a prediction in probabilistic terms. Now, let's do filtering. So you assume that you receive an observation and you correct your prediction. So again, let's use the Bayes law. By Bayes law, the joint probability of xt and yt is the probability of xt given yt times p of yt. Okay, so you can write this formula. That's just Bayes law. Now here you isolate this last term. Okay, this last term. So we have, remember, yt is a sequence. Small yt minus 1, small yt minus 2, etc. So we have this joint probability should be what? Should be, I'm isolating the first term over there. And then I will have y of t minus 1. But I'm conditioning on it as well on xt. And I multiply by its probability density function. Okay, so it's this, this equality comes from isolating the last observation here in this term and using Bayes law. Okay. Now, this term here is the first one there, and then I use again Bayes law. So this p of x y t minus 1 is p of x given y t minus 1 times p of y times t minus 1. So this is nothing more than this joint probability. Okay. Now I observe, maybe I can do it here. I observe that this first probability that appears here, I'm conditioning on xt and then past observation. So since x is Markov, I can cancel these past observations. Okay. And also that last term, this is nothing more than the probability of yt given the past observations. This is independent of xt, so I say it's just, again, it's a normalization constant. So let's put everything together. If you put everything together, what you get? You get this square, this the expression inside this square. So p of xt given the observations of up to t is that kt, which is a normalization constant. Remember that the integral should be 1. The integral of everything here should be 1. It's a density function. Then we have p of yt xt, and then we have p of xt given the previous observation. So this is the predicted density. And this is something, this p of yt given xt is something that depends on the model of your observations. Okay, that's given the state. What do you observe for y? Okay, it's described by this expression here. So our nonlinear filter in general consists of these two operations. You start with the density of the state in the previous time instant, given the observations up to the previous time instance, and then you do a prediction. And this prediction is a convolution integral. And then you correct, you received an observation, and you correct this expression, this predicted density function, which appears here, by multiplying it by this density that depends on the sensors. Okay, that's filtering. I call it filtering or correction. One can approximate to have a practical numerical algorithm, which is not my aim here. One can approximate this integral by a sum and assume that you have the probabilities at given points for given values of x. Okay, that's the point mass filter. These formulas in general, from a computational point of view, they allow you only to solve very simple problems. Okay, so one needs to do some simplifications. But conceptually, they are quite important. Let's see what happens when we say, okay, my system is a linear system with white noise, both in the process noise and in the observations. What happens? And we are going to recover the Kalman filter from these expressions. I should say, do you have a question? But no one answers. Okay, let's go. Okay, so let's look again at the Kalman filter, and we are going to revisit it from this point of view of probabilistic. Let me. Okay, these computations are here, but I'm not going to do it in detail. I'm just going. Sorry, I'm just going to the final result. Then you can do you can read with care the previous slides that I'm omitting because they are not difficult. So what is the point here? When we have a linear system with a Gaussian distribution, okay, with white noise. Suppose that the noise has a Gaussian distribution. Then all the variables will have a probability density function. They will be stochastic processes, and they will have a Gaussian distribution. Okay? So, how do you characterize a Gaussian distribution? By a mean and a covariance matrix. Okay? In the scalar case, it's just a covariance. It's a number. Very simple. I'm going to do the computations in the case of a scalar system. So when you consider this, let's go back to the equations of the filter. When you do these operations, you know that I have a Gaussian. This is a Gaussian. Okay, the probability of the state given the observations up to time t. This is a Gaussian function with some mean and covariance. Okay. Now, what happens when you do these two operations? Well, the convolution preserves Gaussianity. So the predicted density will also be a Gaussian function. And also the multiplication will give you a density function, which is Gaussian, although it's not normalized. So there is a normalization factor that appears, but in the end, the filtered density will also be Gaussian. Now, if everything is a Gaussian, you only need to care about what happens to the mean and the covariance matrix. So this convolution corresponds to some change of the means of these two density functions, okay, that are both Gaussian. And how can I compute the mean and covariance of this function as a function of the mean and covariance of these two that are being convolved. And the same for the product. How can I compute the mean and covariance of this on the left, this density on the left, based on these two terms that I'm multiplying on these densities that are Gaussians, and they have covariances, they have mean and covariance matrices. How can I use them to compute the mean and covariance of this one? Okay. So for that, we need to know this. Suppose that you have two Gaussian functions, and I'm considering the scalar case for simplicity. Okay, so you have two densities for I equal to 1 and 2. So mu1 and mu2 and sigma 1 and sigma 2. mu1 and mu2 are the means, and sigma 1 and sigma 2 are the covariances. If you do the product of these two Gaussians, you get a non-normalized function. That is to say, you need to, there is a constant here, which is also a Gaussian, and the covariance of this product, of this function that is the product, is given in terms of the covariances of the original Gaussians in this way, and the mean is given in terms of the Gaussians of the means and the covariance in this way. Okay. The proof of this result is done in previous slides, so I'll let you read the slides. When you do a convolution of these two the same two Gaussian functions, you get an equivalent Gaussian with mean given by the sum of the means, and covariance, which is the sum of the covariances. In the case of the convolution, it's very simple. Convolution defined according to, according to this integral. Okay. There is still one result that we need to recall from basic probability, which is, suppose that you have a variable, a random variable z, with this probability density function. And from z, you compute another variable, x, such that x is a constant a times, so a is a constant. Okay? And you know the probability for z, you multiply z by a to get x. What is the density function of x? Okay, if z is Gaussian, if z has some probability, that's what I want. So you transform, that's a special case, I'm going there. If x is a transform of z such that it is monotonous, that is to say, suppose that z is scalar, okay? Let's consider it is scalar. Then this function t always grows or keeps the same, but never decreases. And if you know the density of z, what is the density, the probability density function of x, then you will have to, of course, invert the transformation to map z into x. That's the inverse of t. But then you have to multiply by the Jacobian of the inverse transformation. Okay? This is something that is proven in basic probability courses. Now, suppose let's apply this to Gaussian function, okay, with some mean alpha, with mean mu and variance sigma, or sigma square, if you want. And your transformation is just multiplying by a. Okay, if you apply those formulas, you get this expression for Px. That is to say, if Z is a Gaussian function with mean mu and variance sigma squared, then X will be also a Gaussian with mean mu A and covariance sigma A squared. Okay, so these are the results. Now let's apply them to the Kalman filter. And for a scalar case, okay, we could do this for the multivariable case, but the algebra will be much more complicated. So let's do a simple case, scalar. Every x is a scalar, okay? And EW, remember, are noises, and A and H are constants. And the covariances or the variances of E and W are Q and R, okay? R is the variance of the observation noise, of the sensor noise, and Q of the process noise. Now let's do prediction. Okay. From the state model, what happens? We have to compute this density function that appears in the convolution integral of the prediction operation. Okay. So the density of x given xt minus 1 is what? The mean. You see that x is axt minus 1 given, if you are given x of t minus 1, this is, say, constant. Okay? And then you have the stochastic variable e, which has 0 mean and covariance q. So x is a Gaussian with mean a xt minus 1 and covariance q, okay, as here. So I replaced here. So, and I've also rewritten the expression for the convolutional integral that allows you to do the prediction. Now, p of x given xt minus 1 is this Gaussian expression here. So we are doing the convolution. We are doing the convolution of this Gaussian function with this, which is also assumed to be Gaussian. Okay, so we can apply the formulas for the convolution, and we can apply the formulas for the convolution, and we can. This is the formula for the update of mu. Remember that the update of mu was, where was it? Sorry. Here, you just multiply by a, and then this is the formula for the covariance. I'm sorry. No, here. Okay. You apply this formula together with a change of variable, and we here. So we have, this is one should be careful, because here we have to interpret this as a change of variable, because your variable is dxt minus 1. Okay, and then we have the covariance here and the covariance of this one, which is some mean and some covariance. Okay, and if you apply both formulas, you are able to update or compute the mean of the new density and the covariance of the new density, which happens to be the predicted. Okay, sorry. This is better to put the slides one by the other and look at the expressions. So I'll let you to do this. Now, for filtering, I have to look at the relation between y and x. Okay, and the density of y given x, okay, hx will be the mean again, and the covariance will be the covariance of w, because this is when you condition on x, this becomes a constant, and this becomes, and this is the white noise, so it has a Gaussian distribution with zero mean. So P of yx is a density, Gaussian density, with mean hx, okay, because you are summing a constant to the white noise, and the covariance is the covariance of that. Okay. Now, the expression for filtering is a product. This is a covariance matrix which that has as average mu predicted and covariance sigma predicted. Okay, and this is something that has the is mean hx hat xt and covariance r. So you apply the formulas for the product of two Gaussians, and after some algebra you get this. So the algebra is not complete here. Okay. So we now have these expressions that appear here. Okay, this k is the Kalman gain, so actually corresponds to the Kalman gain in the previous, or we have not yet defined it, but it will appear as the Kalman gain. And if you put together these expressions, that you start with a filtered mean at time t minus 1. Okay, so this is the mean of the density of x at time t minus 1, and this is the covariance at time of the density given the observations up to time t minus 1 at time t minus 1. So you update it to get mu pt and sigma p at time t. Okay, so these are the predicted mean and the covariance. And if you put them together with these two expressions, okay, you are able to propagate. You are able to propagate. Now, these expressions, what they do, they receive the predictive ones, mu p, and gives you mu filtered. Okay, so from the mean of the predicted density gives you the mean of the filtered density, and this is the expression that propagates the density, the covariance from the predicted covariance to the filtered covariance. Okay, so you need to define the filter, to propagate these two to use these two equations together with these two equations, and you can combine them and say, well, my my estimate is the mean of the filtered estimate. That is to say, is the mean of the density of xt given, or xt given the observations up to time t. And you can, from those previous observations, you can get this, which is nothing more. You will recognize the Kalman filter. So a replica, first here, a replica of the dynamics, plus again, times the difference between what you observe for yt and what you would be expecting yt to be. This is an example. You can use those formulas. This is an example. So the axis that goes to the right is time, and the axis between minus 20 and 20 is the state. And I don't have here the numbers, but what you have in this plane, on the vertical, you have the densities. This line here that starts at 10 is the true state. Okay, is the true state. And then you have the estimate here that starts at 0, that converges to the true state. And this estimate is nothing more than the mean value of this red Gaussian, which is this is the density function of x of t given yt, given the observations up to time t, all the observations at up to time t. The black densities correspond to what? They correspond to the situation in which you don't do any observations. So just the density of the state, without any condition. And it's, in this case, it's very simple to compute it. It's also Gaussian. And you can see that the red line that corresponds to that corresponds to the estimate, to the density given the observations, is squeezed with respect to the black line. That is to say, a priori, you have some information that corresponds to this black curve. So you have one density at time 10, at time 11, at time 12, 13, etc., up to 20. So I'm representing this only at every 10 samples. And if I were not looking at the observations, but just looking at the dynamics of the system, I could compute the density, okay? And that would correspond just to the predicted density, using the formulas for the predicted density. And this would give me this ambiguity, okay? So the fact that this density is wider or more squeezed is related to the amount of information that I have. The more squeezed it is, the more information I have, because I can find my state with higher probability when these densities are higher. Okay, so the black one represents the probability density of the state with no observations. And then you do an observation, as you can see, you are squeezing these densities. That is to say, you are improving the information that you have about the state. Okay? That's the meaning of the fact that this is more squeezed. Of course, in this case, this is a stable process. If I were considering an unstable process, there would not be no probably meaning, because this density in black would explode. Okay, so the ambiguity will be bigger and bigger and bigger. That's the situation. While the equation for the filter would be under some conditions similar to this one. Any question? This can be, this whole story can be a little bit, well, it's difficult. I mean, many details. So what is important that you retain? I'm characterizing my state estimator by probability density of the state given the observations. Okay? And I can propagate it using two operations, prediction and filter. When I consider the linear case, everything, if I start with an initial error that is Gaussian, everything stays Gaussian. So I can just propagate the mean and the covariance. Okay? And if I get I do the algebra to find this mean and covariance, I get the equations of the Kalman field. Okay? So one possibility of looking at the Kalman filter is the first one that we considered before, the unbiased least variance estimator, and I get some expressions. Another possibility is the story of using probabilities to describe. Okay, and again I get some expressions. Okay? Now in terms of probability. Before we go home, just a couple of slides. In the case, sorry, I repeated my slide. In the case that I repeated my slide, I will correct this. But when we have x of t plus 1 equals to axt plus bu plus some noise, and y equals to cx plus some noise, in general, where now a, b, and c are matrices and x is a vector. Now the Kalman filter can be written in this way. Okay, so it's the expression of the observer, but now you are optimizing the gain using this expression that depends on this matrix P. Okay, this P is sigma here. I should correct this. This P is the same as sigma. So this is a so-called Riccati equation. Okay? It's a quadratic equation that allows you to compute this quantity. And this quantity P is nothing more than covariance of the estimate. Okay? This is the covariance of the estimate. Now, here, sigma or the same P, they depend on time, but you can consider the so-called algebraic Riccati equation that corresponds to the steady state. Okay, this is a difference Riccati equation. Corresponds to the steady state of this equation. Look that this equation is quadratic because, okay, there is k and k transposed, and k depends on p, so there will appear squares of matrices here. Okay, the MATLAB function DLQE do these computations for you, so you don't have to bother about solving these equations. One important thing is, when does this works? Suppose that the covariance matrix of the process noise Q can be written as a DD transposed, where D is a matrix. Okay? If AD is stabilizable and CA is detectable, okay, So C is the observation, is the matrix of observations, and A is the matrix of dynamics. If your initial estimate of the error is a semi-definite positive function matrix, then your algorithm will converge. So, in particular, these two conditions are important for the filter to work and to converge and to give you results, and for the error to converge to zero. Any question? Okay, I will stop here. We are almost done. I would like, in the issue of concerning the issue of state estimation, I would like to speak about two extensions of the Kalman filter for nonlinear systems. As I told you, it's not practical to start with the general nonlinear filtering expressions with prediction and filtering, because the computation is very, very high. It's for most problems, it is impossible to impractical to get results. So we have approximations based on the Kalman filter. So I will present you these two of these approximations. There are many approximations. I've selected two. One is the extended Kalman filter, and the other is the unscented Kalman filter, which I don't know how to say in Portuguese, because unscented means sem cheiro. Don't ask me why it has no scent, or sem faro, better to say. But this is I will spend, say, half an hour in the next lecture to speak about this, and then we will continue to distributed predictive control. Okay, any final question or comment? So see you in 1 week, because next Monday it will be a holiday, so we have plenty of holidays. Bye-bye.
Next week,
I can't hear you.